Alright, in this video I'm going to talk about the shallow water wave approximation and the geostrophic adjustment problem. So in previous lectures we've talked about how large-scale currents in the ocean are in the geostrophic balance. That's a balance where the Coriolis and the pressure force balance each other. But now we're going to study what's called a geostrophic adjustment, which is how is it that if you have a current or a distribution of water that is not in geostrophic balance, how does it end up being in a geostrophic balance? And what we're going to see is that the adjustment involves the radiation and propagation of gravity waves. Okay, so here we were doing the surface gravity waves, so I'm going to change the title to shallow water waves. Shallow water waves. And the approximation we're going to make is that their wavelengths are very, very long compared to the depth of the ocean, and as a result the particle motions are mostly horizontal, very little vertical excursion, and the currents are nearly horizontal. So you have horizontal currents that are to first order depth independent, so there's no variations in z, and we can demonstrate that with the water wave simulation that we've been doing before. In this video, I'm going to demonstrate with numerical simulation that the motions of water particles in the ocean are mostly horizontal with very little depth variation in the limit where we have very long waves compared to the depth of the ocean. And that fact is going to be key to making an approximation called the shallow water equations, or the shallow water waves. Alright, so I've prepared here the water wave numerical models we've been running before. The only changes I've done is I've changed the horizontal extent of the domain. It's now 60 kilometers with a depth of 3,000 meters, and the wavelength I'm going to initialize the problem with is going to be the wave the same size as the domain, so it's a periodic domain, so the waves will just be propagating to the positive x, and what leaves out the right hand side is going to re-enter in the left hand side. And I picked, just to make the particle motions visible, an amplitude of 300 meters, which is very big, but doesn't matter, it's just for illustration purposes. Okay, so let's run the model. Alright, so you'll see that the particle motions are nearly depth independent, and also that the particle orbits are mostly horizontal, so there's a slight vertical excursion but very little. So that means that to first order the w velocities are going to be very small, and also that the horizontal currents are mostly depth independent. And then for this wave, it's a wave of a wavelength of 60 kilometers with a depth of 3,000 meters. A 60 kilometer horizontal wavelength is not particularly big for the large scale circulation of the ocean. So in fact, if I try to pick a wave of, let's say, 1,000 kilometers, which is not unrealistic for the global scale oceans, then you wouldn't be able to see anything. The aspect ratio would be so squished that you just see like a very thin current, but it would just be moving in one direction. You wouldn't be able to resolve anything. So I compromised and picked vertical extents of 3 kilometer and a wavelength of 60 kilometers. If I made it the wavelength even longer and kept the depth fixed, then these orbits would be even flatter, more pancake-like, and more horizontal. Alright, now that we've seen that the currents for these very long waves in a shallow ocean are horizontal, we can make some approximations to the continuity and the momentum equations. Alright, so first we'll start off with the pressure, or the vertical momentum balance. So the vertical momentum balance is hydrostatic, which means that 0 is equal to minus 1 over rho naught dp dz minus g. So no vertical acceleration, vertical pressure force, and gravity. Pressure force per unit mass, force of gravity per unit mass. These two balance each other, and for now, we're gonna neglect any variations in density. So we're gonna assume that the water is of uniform density. If we integrate that equation from the surface down to the bottom, so this is the vertical coordinate z, and the equilibrium depth is h. So z is equal to 0, z is equal to minus h. And if we integrate this equation in the vertical, what we find is that the pressure P is equal to the pressure at the surface, PA, which is the atmospheric pressure, plus rho naught G H minus H, or minus Z. It is minus Z. So this is the integrating this equation, we get the pressure from the hydrostatic, and it's the pressure at the surface, PA, plus in this distance here to here, let me write it nicer. This distance here is h of x, y, and t, I guess. And this distance from here is h. So that the pressure, the weight of the water, if I'm at some point down here in the ocean, let's say at this z, then the pressure is going to be the weight of the water above, right? And this weight is going to be rho naught times g times the height of the fluid column, which is h minus z. And so that will be the weight per unit area of the water above the point z in the ocean. And therefore, the pressure is going to be the atmospheric pressure plus the weight of the water above. And so this fact means that if I want to compute the horizontal pressure gradient, then it will be equal to the following. So if I do the horizontal pressure gradient, that means that grad P is equal to grad pressure of atmosphere plus rho naught G grad H. I guess this is the horizontal gradient, just in the horizontal here. Because we'll need this term for the horizontal momentum equations. And if we assume that the atmospheric pressure at the surface is a constant, then this one vanishes, and what we get is just rho naught G grad horizontal of the deviations of the sea surface height h. And so that means now if we write the horizontal momentum equation, they're going to be the following: dv horizontal dt. And if we include the Coriolis force, we would have a plus f z hat cross vh is equal to minus 1 over rho naught grad p, and any friction term if we want to have any friction term. And that means that this is the horizontal gradient here, because we're doing the horizontal momentum balance. And so we can substitute this in here, and what we have is equal to minus g grad h, the horizontal gradient. And if we were to neglect the Coriolis force, if we assume that we're on time scales short compared to a date, then the horizontal momentum equations are just the following. dv horizontal dt is equal to minus g grad h. And this is for neglecting Earth's rotation. Earth's rotation. Okay, and then the other one we want to look at is the continuity equation. So the continuity equation is div dot v equals 0. And now we're going to integrate this equation in the vertical from h down to the bottom minus h, div dot v. And if we integrate with respect to dz, and this will be horizontal divergence of the horizontal currents times h. Now, when we integrate this one, we're going to use the fact, we're going to make the approximation that we're in the shallow water wave limit, and that V is depth independent. The horizontal currents to first order don't depend on depth. So that the vertical integral of VH is of the divergence is just going to be the thickness of the water column, and we're also going to assume that H, consistent with the linear approximation, that little h is small compared to big H. And so I guess I should put an approximate sign here. So this requires on the fact that VH is independent of Z, and that H is much greater than little h. That is the magnitude. Little h can be negative. Well, either way, even if it's negative, it's much greater. But the magnitude of h is much bigger than little h. So the sea surface height variations are small. We want to be in the linear limit. Just like here we neglected, and also, I guess I should have said, neglecting the non-linear advection terms, i.e. the amplitudes, wave amplitude are assumed small. All right, so that takes care of the angle. In here, to finish this derivation, we also have the dw dz. So we'll also have plus w at h minus w at minus h at the bottom. And now w at minus h, this is just 0. We're at the bottom, so there could be no flow through the bottom. So this one is 0. No flow through the bottom of the ocean. And WH at the surface, that we're going to replace that with just dH dt, right? As the sea surface height goes up and down, the point on the surface is a particle, and its speed is dH dt, right? Or this vertical component of the velocity is dH dt, and it's W. So that means that continuity equation, that divergence of the currents is 0, will become just dH dt plus h times div dot v horizontal. And this is the horizontal component. Is equal to 0. All right, so these two equations, the horizontal momentum equation and the continuity equation, are what we will call the linear shallow water equations, solid water wave equations. So let's do a little bit more with those equations. dH dt plus h div dot vh equals 0. Okay, so what we can do now is, one thing we can do is we can eliminate one of those two equations. So if we do that, we do dH dt, so I'll call this equation 1 and this equation 2. So if I do d by dt of equation 1, what I get is d2h dt squared plus h div dot dvh dt equals 0. And dvh dt from the first equation is just minus g grad h. So this becomes d2h dt squared plus, and the g is a constant, so I could take it out of the divergence. So plus g I guess I could take out the minus g. So this becomes minus gh, divergence of the gradient of h equals 0. So the divergence of the gradient, that's the Laplacian. So this is the same thing as del squared. And this equation, well, I guess the next step is I can define c is equal to square root of gh, and probably you remember that root gh is the speed of the shallow water waves, right? In the limit of very long waves and very shallow ocean, then the speed of the wave is square root of gh. And therefore, this equation over here can be rewritten in the following way. d2h dt squared minus c squared del squared h equals 0. And this partial differential equation is a very famous equation. This equation is the wave equation. This is the wave equation. I mean, it shows up in very many wave phenomena. It's the one that shows up from Maxwell's equations for the propagation of light. Maxwell derived this equation. It shows up in the sound waves. It shows up almost everywhere that we have wave phenomena. We get this equation. So let's do a simplified case. We're going to do a numerical simulation of this one in a little bit, but I want to derive the analytical solution first. It's not so hard, but I'm going to assume that I have currents or a sea surface height that varies only in the x direction. So in the y direction, there is no variation. So we're going to assume that we have waves whose crests are parallel to the y-axis, and there's no variations in the height in h in the y direction. Everything varies in the x direction. And so if that's the case, then assume, so a simple case, then dh dy is equal to 0. So i.e. h is equal to h of x and t only. In that case, then this equation becomes d2h dt squared minus c squared d2h dx squared equals 0. So this is the one-dimensional wave equation. So this is the 1D wave equation. And it is also the one equation that would describe, for example, the waves on a rope. Perhaps you saw in your physics class in high school. If you take a rope and you tie it and it's taut, and you give it a swing and the waves propagate back and forth on the rope, then they would satisfy this equation, the one-dimensional wave equation. Okay, to solve this equation, we can notice that this equation can be rewritten like this: d2 dt squared minus c squared d2 dx squared h equals 0. And this looks like a squared minus b squared, or a square minus a square, or a difference of squares. And if you remember from your algebra class, a squared minus b squared can be written as a minus b times a plus b. And we can do the same thing with this operator. We can factor the differential operator into d by dt minus c d by dx times d by dt plus c d by dx. H equals 0. And the reason this is useful now is that if the first operator acting on h is 0, then we have a solution. Or if the first operator acting on h is 0, we also have a solution. And these two, they commute. We can interchange the order of these two differential operators. I could have factored it to get first the plus, then the minus. We get the same differential equation. And so let's look at solutions of either case. So case 1. Case 1, dh dt minus minus c dh dx is equal to 0. So I claim the solution is h of x and t is equal to f of x plus ct. Let's verify. If I do dh dt, that will be equal to f primed of x plus ct times the derivative of the inside. So dx plus ct with respect to t is just a c. And if I do dh dx, that's equal to, again, f primed of x plus ct, and the derivative of the inside with respect to x is just 1. Now if I multiply the second equation by minus c and I add, so I get minus c, add the two, what I get is dh dt minus c dh dx is equal to c f prime minus c f prime equals 0, and therefore I have a solution. So one solution is just any function. This is true for regardless of what f is. So is some function whose argument is x plus ct, and this corresponds to a wave propagating to in the minus x direction, right? So as t increases, x has to decrease if the argument is going to be, if f of the argument is going to be a constant. So as t increases, the value of the function gets translated to the left. All right, so and then case 2. Case 2. Oh, I should keep the solution, I guess, right? h of x and t is equal to f of x plus ct. Case 2 will be dh dt plus c dh dx equals 0. And this time I claim that h of x and t is equal to some function g of x minus ct. And let's check. dh dt is equal to g primed of x minus ct times minus c. And dh dx is equal to g primed of x minus ct. And the derivative of the inside with respect to x is just 1. And now if I want to check this equation, if I multiply the second equation by plus c, and I add the two, what I get is dh dt plus dh dx times c is equal to minus c times g primed plus c times g primed is 0. And therefore we have a solution. So in this case, h of x and t is equal to g of x minus ct. And this one is a wave propagating in the plus x direction to the right, right? Because as t increases, this becomes more negative, and if the value of g is going to be a constant, then x has to increase, and you get a pattern translating to the right. And so the most general solution will be of this form. So if the wave equation, the 1D equation is d2h dt squared minus c squared d2h dx squared equals 0, that implies that h of x and t is equal to f of x plus ct minus, or plus g of x minus ct. And so the wave is a pattern that propagates to the left plus another pattern that propagates to the right. And we will see this when we do the numerical simulations. All right, I also want to write down what the momentum equation, what were the equations that led to this equation in the 1D case, because we're going to write the numerical model using the original momentum equation, not for the wave equation itself. And so if I go back to the 1D momentum equation, we have the following. du dt is equal to minus g dh dx, and I'm going to ignore the v momentum equation, and then dh dt is equal to minus h du dx. So this is the momentum and continuity equation in the 1D case where there's no y variation. If I do want to retain the Coriolis force, then the equation becomes the following. So if we bring back the Coriolis term, in other words, if we don't neglect it, then the first equation becomes du dt minus f times v is equal to minus g dh dx. And the v momentum equation is dv dt plus f times u is equal to, and if we still neglect the x variation, then minus g dh dy, right, that would be what would appear here. That is going to be 0 because we have no y variation, it's just 0. And then the continuity equation would be dh dt plus h times du dx plus dv dy, but no y variation, this is still just du dx equals 0. So this is with the Coriolis force, this is without. Now if we want to add friction, we can do that, assuming that the friction is just like a body force, because the shallow water equations assume that u and v have no vertical variation. So if we put a friction just at the bottom of the ocean, then that would cause some shear because the currents would have to go to 0 at the bottom of the ocean. So just a simple mathematical model to do this would just be to add just a friction, which will retard the flow in the whole flow, like over the whole water column, just times u, because u has no variation. And if we did the same thing in the in this momentum equation, the minus r times u minus r times v. So that would be the friction in the y momentum equation and in the x momentum equation. All right, we'll get to see all these things when we go to the computer.